Today we are going to begin extended material. We are going to start in our new books, which are Book 0, Chapter 12. So we're going to start talking about sets in geometry. So usually when we think of geometry, we think of geometric figures. Here I have two intersecting lines, and this would be the usual drawing I'd have for them. A lowercase letter to identify each line. So this is line L, this is line M, they intersect at P. But really a line is a set of points. So I can also use a Venn diagram to display the relationship between line L and M. And it is here, and because it was hard to draw hatching, I am going to draw it in now. So this says I have two lines, they intersect in a single point. The hatching indicates that the only point drawn there is the only one in their intersection. And then I can have infinitely many points outside their intersections, here and here. Here's another drawing, and I want you to try to draw yourself a Venn diagram that would go with that. We have plane pi and point P and line L. So we would need two circles, one for the line and one for the plane. Give it a try, press pause on your video feed. When you're ready for the answer, press play again. Here you can see I have a circle that represents my line. I have a circle that represents a set of all points in my plane, pi 1, and they intersect in exactly 1 point. So I've drawn in the point and named it. I've put the hatch marks there to indicate that there's not one other point that's in the intersection. This time, this gives us the Venn diagram, and they want us to draw the usual diagram. So whenever you see a lowercase letter, that's going to indicate that it's a line. So I have line L and M. Hatch marks may or may not be present. And I want you to try and draw the drawing that would go with this Venn diagram. Press pause, and when you're ready for the answer, press play again. The only way that I can have two lines intersect in 2 points is if they are the same line. So if I wanted to add appropriate hatch marks to my diagram, I could put them on the outsides. But remember, our book doesn't always draw the hatch marks. Sometimes they do. We always have to draw the appropriate ones. Now, I want you to turn to page 34 in your book, and I'd like you to look at figure 6. I did my best to replicate it in this drawing here, and you'll notice that I have green and red actually in the book, so it's going to be in color, and the green and red mean something. So this is a set of points on a plane. The green indicates that the points belong to figure F. There's F. And the red indicate that it does not belong to figure F. White in the picture indicates that it does not belong to figure F. So now I'd like to talk about interior points, exterior points, and boundary points. Interior points are green, and everything surrounding them is green as well. So if I look at point P, that's green, and everything around the outside, everything that touches P is also green or part of my figure. So that is an interior point. Let's examine the other points. So let's see. I see that S is also green or part of my figure, but everything around the outside of it is not. So that is not an interior point. Q, same kind of problem. Q is green, but not everything around it is green, so that is not an interior point. The only interior point in this figure is P. Now, the exterior points are points that are red, where everything around them is either red or white. So let's examine some points. If I look at R is red, and everything around R is white or not included in the figure, so that is an exterior point. Let's look at Y. Y is red, but everything around the outside of it is green. So that is not an exterior point. T is also red, but I have some points next to it that are green. Therefore, that is also not an exterior point. The rest of the points in this figure that are named are boundary points. So let's take a look at what a boundary point is. If I look at point Q, it's green, and around the outside of it is both green and red. So that is a boundary point. The boundary point can be either green or red. So, for example, if I look at Y is red, but everything around it is green, so that is a boundary point. And let's see what else. S is green, but everything around it is white, so that's a boundary point. And finally, Q is green, but some around it are white or red, and some are green, so that is a boundary point as well. There are other points in this figure, although they are not named. For example, I could name any other point in here. For example, I could put another point here, V. What do you think that point is? Interior, exterior, or boundary? It is in the interior, it's green, and everything directly next to it is green as well. For example, everything that existed in this world for the figure was on a flat surface or on the plane. However, in this now, that was relative to the plane. In our last figure, same picture, we're no longer just dealing with the sheet of paper or the plane, but we have to imagine that this figure is floating in space, and we have to determine which points are interior, exterior, and boundary points. So rather than just looking around the outside of it, we also have to look to the front of a point and to the back of a point. This is paper thin, even thinner than that because it's just location in space. Everything in front of this figure is white. Everything behind the figure is white. So interior points relative to space of my figure F. There is not one single point on here that is in the interior relative to space. But I have some points that are exterior points. For example, R is an exterior point. It's red, and everything around it is not included. So R is an exterior point. And if I look at T, that's not exterior because I have some green next to it, and in the front it's white, red, all over the place, so that's going to be a boundary as well. Every other point on here is a boundary. Even S, it's green, but right in front of this point is white, and behind the point is white. So rather than looking at a little disc surrounding each point, as we did in the previous problem, we have to think about looking at a little sphere around it. So all the other points in this figure are boundary points. So that would be Q, Y, P, T, and S. Now we need to talk about a closed set versus an open set. In order to determine whether a set is closed or open, we consider the boundary points, the set of all boundary points. So if I look at the definition of a closed set, it says a set is closed if and only if for boundary points in G, boundary points relative to a ground set of F are a subset of F, and the boundary points of F relative to the ground set G are not the empty set. So what does that mean? It means all boundary points are part of the figure. So in order for them to be part of the figure, all boundary points that exist in the figure must be green. The next definition says that a set is open if and only if for boundary points relative to G of F that are subsets of G minus F. In other words, boundary points that are not part of the figure. And boundary points are not the empty set, so there has to exist at least one. So in this case, what that means is all the boundary points that exist are red. Now, if there's no boundary point that exists, then it is both open and closed. If, on the other hand, I don't like that. Black would be better. Some boundaries are green and some are red, then it's neither open nor closed. Now, let's go back to if there are no boundary points and they're both open and closed, because that is usually what students have difficulty understanding, but I think you'll get it. So let's look at the definition for closed set. I'm going to write it in a little bit more of everyday language, and I'm going to write it in just one direction. If there is a boundary then they are green. Now think back to your knowledge of if-then statements. The only way I can say that statement is false is if the first part is true and the second part is false. So an if-then statement is only false if the first part is true, implies the second part is false. Well, if there are no boundary points, actually I want to rewrite this a little bit. Hold on. Let's go back. If it is a boundary point, then it is green. So we'd have to be able to say that for every single boundary point in the picture. Well, if there are no boundary points, you would never get that first part to be true. So this would be false implies something, but in those cases, if-then statements say false implies true and false implies false are both true statements. So if there are no boundary points at all, then they are both open and closed sets. Now, let's take a look at our picture again. And it says if it's asking us if F is open or closed relative to the plane. Well, we had several boundary points, right? And we have to even consider boundary points that are not named. So if we have some boundary points that are red and some that are green, then it's neither. So as I look at this, Q is green, it's a boundary point. Y is red, it's a boundary point. Every point along here is also a boundary point. So we have a mix of colors. So therefore it is neither open nor closed. Now we're going to look at it relative to space. So thinking back to our last picture, every point on here is a boundary point relative to space. So therefore, well, except that one, that was an exterior point. All these points are boundary points, and I have a mix of colors. So this is the same thing. Neither open nor closed. Now, this is part of your homework and also part of the video, and I'll explain it in a minute. I want you to look at each of these sets, and I want you to determine whether or not the set is open, closed, neither, or both. This is on page 41 of your book, and I just want to make sure you understand that a circle is a set of points that are equidistant from a center point. It does not include the inside. So it's just the points along the edge here. However, a disc is a filled-in circle. So you have to think of the disc as every point is inside as part of that figure. Okay, so take a minute Decide what each set is, open, closed, neither, or both, and then press play on your video feed and check your answers. Okay, a circle is closed. That's because relative to the plane, every point is included in the circle. These are all boundary points, and they are all green, so therefore it is closed. A disk with its center deleted is neither, and that's because, last figure I drew the disk, but I didn't delete the center point. Let's see if I can draw that. Okay, I'm going to draw it again. So, here's my circle, and it's a disk with the center deleted, so I'm going to shade everything in, but then I'm going to delete the center. And I really could draw this green. It should be green according to our color convention. And the center is deleted. Okay, so as I look at this, every point on the outside here is a boundary point. They are all green, included in the set, and the center being deleted is white, or I could have made it red as well. So that is red. So this is neither open nor closed. All my answers went away. If I look at a circle with one of its points deleted, so I'm looking at that circle with one of its points deleted. This is neither as well, because around the outside of it, those are all boundary points, but the red point is boundary point as well, so it's neither. A line segment is closed. Every point on that line segment is a boundary point relative to the plane. Therefore, every single point is green. Part of that line segment is closed. Letter E says I have a line segment where my endpoint is deleted. So I have P and Q, but that P is deleted. So every point along that segment is a boundary point, including the point P, and therefore it is also neither. Pi, relative to plane pi, there are no boundary points, so it is both. An empty set, there are no boundary points, so that is both open and closed. Okay, next I want you to do the homework that I've posted online for you. Have a great day.